The next thing we're going to talk about, now that we have the driver behaviors out of the way, if you remember, I was saying that, if you think of your traffic flow theory, flow equals speed times density. We looked at the density component. Now we're going to look at the speed component. So if you get your driver behaviors calibrated correctly, then you are correctly calibrating the density on your links. And then if you get your speeds calibrated correctly, between those two, then theoretically your capacity values should be fairly close to what you'd see in the field, right? Or maybe it's a new build or new facility that you don't know what the capacity is. Well, calibrate the driver behaviors, i.e. the density, and calibrate the speeds, and that will output a capacity that you can then reliably use, because you can justify using the density and speeds to give you a capacity result. So we're going to look at the speed settings next. Speed settings, this is straight out of the protocol. Best practices recommend generating desired speed distributions from existing field data for existing condition models and for future models where the geometry is from the existing conditions. So what we are saying there is that the input speeds that we are entering onto the vehicles need to be derived from field data to give you a nice, good, accurate result. Um, Now in Vissim, there are two types of speed that is utilized in the simulation. We have something that we call desired speed, and we have something that we call simulated speed, or it's just indicated as speed in Vissim. The desired speed is the uninterrupted speed of the vehicle. It's the speed that the vehicle wants to go if it had all green lights and there were no cars in front of them. Imagine, a good analogy for this is a car driving home from work at midnight, right? You're off the graveyard shift, you're coming home at midnight. There's no other cars on the road. How long would it take you to get home, right? You're going to set your cruise control to something and you're just going to go. That's your desired speed. And then once we start adding in congestion or slower moving cars ahead of you or signals, that's going to drop your actual speed or your simulated speed down below your desired speed. And this is very important that we differentiate between these two. So if you're looking at your field data, you might be looking at like a peak hour congested condition, right? It's important to remember that none of those cars in that stop and go traffic want to be going 25 miles per hour, right? If they're on the freeway, they might want to be going 50 or 65 miles per hour. So their desired speed is going to be 65. So the input speed that you're going to enter is 65, and then you're going to get your output speed of 25, assuming everything else is calibrated correctly. And the difference between your desired speed and your simulated speed is going to be how Vissim records delay. So unlike something like HCM, Highway Capacity Manual, or anything like that, where you input a capacity or a saturation flow rate with adjustment factors and green times, and then that equation spits out an average vehicle delay, Vissim does it again in reverse. What you do is you simulate the driver behaviors, you simulate the interactions between vehicles and infrastructure, and you simulate what speeds they want to be going, and then you measure their actual speeds as they traverse your network, and you compare the two, desired speed to actual speed, and that gives you your delay, because the desired speed will produce a specific desired travel time throughout the network, and then the simulated speed will give you your actual travel time. And the difference between your desired and your actual travel time is the delay experienced by that individual vehicle that then is aggregated into larger facility level delay results. So in this case, the reason I'm harping on this so much is because it's a very common practice, or not practice. I don't want to say. It's not uncommon for modelers to look at the field data and say, well, the field data says the freeway should be going 25 miles per hour during the peak hour, so I'm going to set the desired speed to 25 miles per hour. The problem with doing that is, let's say you're doing a new build option where you add a lane or two, or you add some sort of new build to improve the flow. Well, you're going to add that, but the desired speed is the maximum speed that cars are going to want to go. So if you set your desired speed to 25, regardless of any improvements you make, they're only going to want to go 25. Or the alternative is you make those improvements and then you artificially inflate the desired speed to whatever speed you assume they're going to be going. And then that just kind of defeats the whole purpose of running the simulation, because now you're making a massive assumption about how effective that facility is going to be. So what you want to do is you want to set your base network's desired speed to free flow conditions or off-peak conditions, or whatever speeds you anticipate that the vehicles would go if they had free flow, steady state flow. And then you would compare that to your congested speeds and model other things like driver behaviors, lane change behaviors, um, volumes, uh, signal timing, gap acceptances, things like that, to produce those congested speeds in your base model. And then once you have all that done, that's a good indicator that you have calibrated your network correctly, because now your output speeds are matching your congested speeds. All right, so the way we implement speeds, now that I've talked about desired speeds and simulated speeds to death, um, the way we implement speeds in Vissim are in two ways. One is with a desired speed distribution or decision point. This is like a speed distribution around some sort of posted speed limit, right? So verify the desired speed distributions for existing condition models are generated from existing field data, or reflect uncongested speeds, right? So in this case, we're going to go into the base data menu and look at distributions for desired speeds. And then we're going to have different desired speed distributions for different parts of the facility. And these are independent from the links. These are kind of like anywhere where a posted speed limit sign is, or anywhere where a facility type changes. We're going to see all the locations where these should be in a minute. But what we do is we assign a desired speed distribution to that decision point. And the distribution sets up a minimum desired speed and a maximum desired speed. So in this case, a posted speed limit of 65 miles per hour, that would be like you as a driver looking at a sign that says 65 miles per hour. Now, every driver has a different perception on what that posted speed limit means to them as a driver, right? Another way to think about this is if you are driving down the freeway and the posted speed is 65 and you are in the left lane and you are going 65 because the car in front of you is going exactly 65, are you happy about that situation, or are you angry about that situation? If you're angry that you are going exactly the speed limit in the left lane, that tells you that your desired speed is on the higher end of the curve. If you are that person, or if you are okay with that person going 65 in the left lane, then that means that your desired speed is probably on the lower end of the curve, or maybe in the middle of the curve, or something like that, right? So everyone has a different acceptable risk that they are willing to take as drivers, and that's reflected in this desired speed distribution. So what you'll do is you'll collect data, or the modeler will collect data from the field, um, and they will take that free flow, uncongested speeds conditions, and they will match a speed distribution to match that data. They'll get a percentage of the vehicles that are going between 50 and 60, and then they'll get a percentage of vehicles that are going between 60 and 70, and a percentage of vehicles that are going between 70 and 80. They'll enter that into our speed distribution, and then when Vissim runs the model, cars are going to run over that decision point and be randomly assigned a speed somewhere along this distribution based on their aggressiveness. Um, Then we're going to verify that the speed distributions for future models use ranges outlined in the protocol. Now, for future models, this gets tricky because you might not have you might not have field data for that facility, because maybe you're adding a new roundabout, or you're adding a new bypass, or you're punching through an arterial or something like that. Um, so you might not have field data that you can compare it to. So the Vissim protocols give you guidelines on what these ranges should look like for future conditions. And so I'm not going to necessarily read this out to you, but they are in the protocols, and there are some guidelines, some guide rails to work with. Common ones though are using 85th percentile speeds, plus or minus 5 miles per hour, kind of things like that. So once we've checked the desired speed decisions, the next thing we're going to look at are verify that reduced speed areas are used on turns and other temporary speed reductions. So desired speed decisions are like posted speed limits, and reduced speed areas are like advisory speeds or assumed speeds for specific maneuvers, right? So imagine you're driving down a rural highway. There's the white posted speed limit, and then there's the yellow sign that says curves ahead 45 miles per hour. That curves ahead sign would be indicating a reduced speed area. Or maybe you're coming into a neighborhood and there are speed bumps or studs or something like that, some traffic calming devices to get vehicles to temporarily slow down on a section of the roadway. Or, think about an approach to a roundabout, right? It's going to have a flare, a deflection to slow vehicles down coming into the roundabout. Um, so those are all examples of reduced speed areas. And they function very similarly to desired speed decisions, except for the fact that a vehicle is going to have a desired speed ahead of time. They're going to look ahead and they're going to say, I need to make a right turn. So I need to slow down to whatever the speed limit is on this turn. And then while I'm making this maneuver, I slow down. And then after I've completed the maneuver or left this yellow box, I can accelerate back to whatever speed I was going before. So that's what a reduced speed area is. And what we want to look for are these traffic calming devices being accurately created with reduced speed areas? Are the turns accurately modeling the speeds of the turns? So, because again, capacity is a function of speed in Vissim. So if your left turn doesn't have a reduced speed area, people are going to go flying through that left turn. Whereas having a really sharp right turn is going to have an inherent slowing effect on vehicles, which is going to limit the throughput. So let's go ahead and take a look at all of our speed settings within our model. I'm going to close my driver behavior. Oh, before I close my driver behaviors list, I'm just going to save my attribute file. I'm going to hit save. There we go, just so we can keep that there. All right. So now I'm going to use this drop down and I'm going to find our speed selection. So we have existing and future speed decisions. These are going to be very similar. But what we're looking for here are reduced speed areas and desired speed decisions. In this case, we're looking specifically for desired speed decisions. And again, similar to other areas, we want to open our desired speed decisions list. And again, the desired speed decisions are indicating posted speed limits or facility level speeds that might not always be posted, but the laws and regulations say unless otherwise posted, or rural highways are always 55 or something like that, right? Um, so there might be some common knowledge speeds and things like that. So in this list, I'm going to use the single list option. And what we have desired speed decisions spread out through the network. And in this case, the modeler did something that I really like as a reviewer, and they went ahead and they named their desired speed decisions. You won't always get this lucky. Sometimes, more often than not, these are just empty and blank. So you just kind of have to go look at where you are in the model. But for example, we could look and, okay, this is a freeway element and the posted speed limit is 60 miles per hour. So in this case, we can then look in this column for the speed distribution 10 and speed distribution 20. What these are indicating are the speeds for the vehicles that are of class 10, which in this case is car, and the speeds for vehicles of class 20, which in this case are trucks. So the truck speeds and the car speeds, and both of them are assigned the same mainline basic 65 miles per hour. So where do we find this mainline basic 65 mile per hour distribution? We go into base data, distributions, and desired speeds. And in this list of desired speeds, you can see all of the speeds that were created for this model. You can see an upper and lower bound, but if you double click, in this case, we are looking for our mainline basic 65 miles per hour. You double click on it, and that will open up the distribution window, and you can see the distribution that is assigned. And again, this is the maximum speed or the free flow speed. So under uninterrupted flow conditions, what choices our vehicle is going to make as far as speed goes. In this case, it's between 50 and 80 with breakpoints at 60 and 70. So if we look here, this is close to 60 and it says 0.22. Well, that's indicating the percentage of vehicles that are going less than that speed. So in this case, 22% of vehicles are going to want to go less than 60 miles per hour. If I hover over the next one, 84% of vehicles are going to want to go less than 70 miles per hour, and then 100% of vehicles are going to want to go less than 80. You can also look at this by clicking on it in the list, and you can see these data points here. The reason they're not perfectly exact is because when you create it, you can kind of just drop the dots close, and it might not be super on the nose, but that's okay. That won't really affect your simulation too much. But you can also take a look at those values here. Let's go to a different spot in the network and take a look at something like an arterial. So here we have this roadway right here. It's a 35 mile per hour arterial desired speed distribution. So I'm going to select this 35 mile per hour. We can see that it looks like this, but if I open it up, we can see that it's going somewhere between 30 and 45. And then, I accidentally edited it. Didn't want to do that. I just want to hover over it. 22% of the vehicles are going less than 36, and 86% of the vehicles are going less than 40. So that's the kind of investigation that you're going to do. One way that we could improve this layout is to go ahead and activate the labels. Now, the hard part about the labels, why I didn't have them activated earlier, is because there's a bunch of desired speed distributions or decision points that are all stacked on top of each other. So you have to zoom in pretty close to be able to see them apart. But this will give you the ability to see, okay, this is number 69. So you can find desired speed decision number 69 in the list. You could also come into the graphic parameters. If we click this graphic parameters button, we can change the label attribute to show something like the speed of cars, right? So the post speed limit for cars, for example. And what this will display is the desired speed distribution that is being used. In this case, it's using desired speed distribution number 1 for the cars. We can see that that's our mainline 65. So this could be a shortcut way of being able to spot check your network and see what type of speeds are being used. Another label that we could do is maybe instead of the number, we look at the desired speed distribution, and we look at the first one in the list, and we look at, what am I trying to say? Oh, we actually want the name. Let's just do the name. There we go. So 60 miles per hour, 50 miles per hour, things like that. So for the label, I just picked the name object for the label. And since this modeler was really good about naming all of their desired speed decisions, this makes our job even easier because now we can just look, okay, this is posted speed limit 50 for this ramp. That makes sense. This is posted speed limit 60, 35, 45, 35. And what you're going to look for is for these desired speed decisions, anywhere where the facility changes. So not necessarily from link to link, but we're going from a freeway to an off ramp. There should be a new speed for that new facility. We're going from an on ramp. We see on this ramp, we have a 50 mile an hour as they enter the on ramp, and then a 60 mile per hour as they enter the freeway. What you'll notice is that this 60 mile per hour is offset away from the freeway a bit. And that's because cars will cross this point and then have to accelerate from 50 up to 60. So the modeler is giving those drivers a little bit of time to accelerate, so that by the time they hit this acceleration lane, they're already going 60, which can improve the flow rate a little bit. But that's based on the behavior of the drivers. If you've ever driven in Portland, we would model this by taking the 65 mile per hour and putting it all the way at the end of the acceleration lane, because people are terrible at accelerating here. Um, so that's just a anecdote. But for example, on a Clover, 35 miles per hour, and they're going 60. They're going to hit this Clover, and then they're going to start slowing down to 35, and then they're going to accelerate up to 45. And so you're just looking for, do these desired speed decisions make sense for the facility that they are being used on? For future conditions, you'll do the same thing. This is the same checklist, same graphic overlay. It's just, you might have, this is just a reminder that this is part of the checklist, but it'll be kind of the same thing. So for existing conditions versus future conditions, the big difference between the two is, for existing conditions, you're comparing to field data. For future conditions, if it's a new facility, you have those estimates that we talked about in the PowerPoint. The last thing, for checking reduced speed areas, we're going to look for attributes in the model that the reduced speed areas are using. So we're looking for areas where vehicles are temporarily slowing down. Now, another key aspect about reduced speed areas, if I zoom in on this Clover interchange right here. Now, I just mentioned how desired speed decisions, the cars cross that yellow line and then have to accelerate or decelerate after crossing that yellow line. Well, a key distinction between a desired speed decision and a reduced speed area is a reduced speed area. If I click on a desired speed decision, it has vehicle classes and speeds associated with it. That's it. If I click on a reduced speed area, it has a vehicle class, a speed distribution, but it also has a deceleration value. And so what that means is that vehicles that are approaching this exit, that their static route says, I need to take this exit, they're looking onto the exit and they're seeing this reduced speed area, and they're saying, by the time my front bumper hits this yellow box, I need to be going 25 miles per hour. So what they are going to do is they are going to pre-plan their deceleration rate at this rate that is indicated on the reduced speed area, and they're going to start decelerating at that point. So for a just for a demonstration, I'm going to turn off the background map just so you can see a little bit better. And I'm going to get my pen tool out just so you can kind of see what's going on. Let's say that we have a graph here for this exit lane, right? For this exit, where we have the speed of the vehicle based on the position of the vehicle, right? So if we only had a desired speed decision at this location right here, what would happen is the vehicle's desired speed would look something like this. Why does it say signed in right there? That was weird. Okay. Um, I'm not sure why it said it was signed in. That was an odd thing. All right. Oh, that's just probably because I started my pen tool. Okay, cool. All right. So we have our speed. We have our desired speed decision. And then our desired speed, which I'm going to indicate in green, is going to look something like this. They're going to go all the way up to here. And then when they get to this desired speed decision here, their desired speed is going to drop. But their actual speed, sorry, I'm going to redraw this just one more time, just so it's a little bit better. There we go. Oh, that was even worse. Sorry. Here we go. Like this and like this. And then I'm going to put a desired speed decision right here. So what their desired speed profile is going to look like something like this. and it's going to be at 60, and then it's going to drop down to something like 25 or 35. But their actual speed curve, if they weren't following anybody, would look something like this. So they're matching their desired speed, they cross that line, and then they start to slow down to 25 miles per hour or whatever this curve speed is. But you'll notice that they're already like driving into the curve, still going 65 miles per hour and then slowing down. Now, A, that's going to be really dangerous. It's probably not going to replicate real life. And you're ignoring the fact that vehicles might actually be slowing down on the freeway, causing freeway congestion because they're preparing for the sharp curve up ahead. So what I'll do is I'll draw a new line, and I'll draw it in, I'll just erase it. So what the reduced speed area does is it will do virtually the same thing, but the key difference is the start of the reduced speed area looks like this, and the vehicles are going to slow down in anticipation of it. So just like before, the desired speed is going to drop, but the actual speed, since this has a deceleration rate, there's going to be a deceleration curve that is plotted backwards from the desired speed decision. So their desired speed will be somewhere over here. They'll hit that curve and they'll start to slow down to that point. And if the vehicles are going slower, they'll drive along and then they'll drive a little bit further, but they'll still hit this deceleration curve and they'll slow down in anticipation. So what that means for us is that cars are going to start slowing down, I don't know, like right here, or if they're going 65, they might start slowing down right here. So that way you're making sure that cars are going the correct speed by the time they hit the ramp, but they're also slowing down in anticipation of this sharp curve up ahead, which could create congestion on the freeway that is more realistic in the simulation model. So that's another feature of reduced speed areas and why we see reduced speed areas on the curves, as well as some of these other ramps and things like that. So from this list, just like we did with desired speed decisions, we're going to open up the reduced speed areas list. And in this case, they didn't name the reduced speed areas. Not necessarily all of them, at least. They have some that are called left turns. They have some that are called right turns. And they have some that are called 25 mile per hour and things like that, but they have a bunch of blank ones as well. So some of these blank ones might be ramps or something like that. But what we're going to look for is, again, the desired speed that is assigned to cars and the desired speed that is assigned to trucks. And then that deceleration rate is another big one. So we're going to want to look for those deceleration rates and see if the default is 6.56. If that deceleration rate is higher, what that means is that vehicles are more willing to slam on the brakes at the last minute and then navigate that curve or that reduced speed area. If it's lower, they're going to slow down much more quickly. So if we're looking at something like this exit ramp and you have field data that says congestion should go back to this point right here, but you're simulating and the congestion goes back to this point, what you can do is you can decrease the deceleration rate so that cars start to slow down sooner, so it kind of spreads out that traffic a little bit. And so you can kind of calibrate your lane utilization, you can calibrate your congestion level using reduced speed areas. And then the final component of this is we have the labels active, but in addition to the labels being active, we've colored the labels based on whether they're using the default deceleration rate or if they're more cautious. So if the deceleration rate is lower or if it's higher. So in that way, we can identify if there have been any calibrations done. So at a glance, we can see that pretty much all the reduced speed areas are white, meaning they're all using the default value. So we don't even really have to scroll through this list. We can just assume that they're all using the default value.